This is 4.3.14, but we're doing some clarifications from yesterday. So in talking about saturated and supersaturated solutions, if we have 100 grams of solute in here, and this is saturated at 20 degrees Celsius, but we've managed to get 110 grams in here, and it's also at 20 Celsius. This one is supersaturated. That's terrible writing, but it contains more solute than the saturated one does. This thing is clicking on and off randomly. Okay, so hopefully that takes care of it. If you've got more questions, bring them up as we go. What we have here is a solubility table. Different values, different numbers of grams of solute that you can dissolve at varying temperatures. So you'll probably see some questions on your next FIP, which I would anticipate probably tomorrow or Monday, on creating a saturated, unsaturated, or supersaturated solution. So using a solubility table to look up those values. So here's where we get into what will dissolve what. Solute-solvent interactions. Not everything will dissolve everything else. And the key word is, or the key phrase that people usually use to remember this is, like dissolves like. So things that are polar will dissolve ionic compounds because they're made up of charged particles, and polar molecules have charges. So like dissolves like. Things tend to dissolve things that are like them. Take the example of water and oil. Are those two things going to dissolve in one another? Now, if you put water and oil together, you can shake it up and they'll mix for a little while, and then the water molecules are going to be so strongly attracted to one another that they squeeze out all the oil, and pretty soon you have a layer of oil on top. So they don't mix. You'll get a layer of each. Water's polar, oil is nonpolar. They don't dissolve in one another. If you've got any kind of ionic compound, it will dissolve very nicely in water. Ionic compounds are highly water soluble because of that charge on water, that partial charge. It gets in and attracts itself to all those ions and separates them and breaks them up. Typically, if we take an ionic compound and put it into a non-polar solvent, like oil, gasoline is a non-polar solvent, any of the organic compounds, ionic compounds will typically not dissolve in those. So you can put, hence, sugar or salt in a gas tank. It doesn't dissolve in there. It does not make a solution. It's, it just kind of is crud and chunks in there. So remember we said that solutions are more than dissolving a solid in a liquid. We have liquid-liquid solutions. And so if you take water and vinegar, can you dissolve vinegar in water? Yes, you can. If you take oil and water, we just said, can you dissolve oil in water? No. When we're looking at two liquids forming a solution, we really are almost talking about them mixing. It doesn't look the way we think of dissolving. It is, but it doesn't look like dissolving to our minds. So what we talk about is miscibility. M-I-S-C-I-B-L. Right? Okay, so miscibility. And this is the ability of a liquid solvent to dissolve in another liquid solvent. If we have two things that don't mix, oil and water, that is immiscible. Okay, so pressure. Does pressure have a big effect on liquids, like on their volume or anything? Does pressure have a big effect on the volume of liquids? Can I compress water? Not really. It's not very compressible. Does pressure have a big effect on the volume or the state of things that are normally gases? Yeah, it's huge. We can make, as you remember from your phase diagram, we can make CO2 into a liquid under, significant pressure, but at room temperature. So when you up the pressure, it doesn't change how soluble liquids and liquids are. It doesn't change how soluble liquids and solids are. However, if we are attempting to dissolve a gas into a liquid, and our favorite example is pop. Yeah, my badly drawn pop there with our what gas in it? CO2. Under higher pressure, we can dissolve more gas into the liquid. So, pressure up, the solubility up, which means they are what kind of proportional? Directly or inversely? They are directly proportional. So when and we'll put our little CO2 bubbles in there, we get it under enough pressure that the CO2 is actually behaving as a liquid. It's in liquid form in the pop. We talked about pressure and solubility. The other thing, of course, the obvious elephant in the room is temperature and solubility. And again, with solids and liquids, liquids and liquids, it doesn't make much of a difference. You can heat up olive oil as hot as you want it, add it to water, it's still not going to be miscible. Temperature doesn't make a big difference. Temperature, it makes a difference in how fast a solution will, how fast you can dissolve something, and it makes a difference in how much solid you can hold, but it doesn't make a difference in the same way that it does with gas solubility. So it's important in liquid solid solubility. It's overarching, important, and fundamental in gas solubility. So if we up the temperature, the liquid can't hold very much gas. And you all know this intuitively because if your pop is warm, it's flat rather quickly. You can keep it cold and open in the fridge and it'll stay nice and bubbly. If you leave it open on the counter and it's warm, it's going to bubble right off. Solid solubility in liquids is, we say here, somewhat less predictable. Typically, increased temperature means increased solubility. There are a few exceptions. I'm not even going to go into those. Generally, it's a direct relationship. So, when we talk about solutions, we have to have some way to measure how much stuff is dissolved in how much other stuff. This is measuring the concentration of a solution. So you all know that there's a huge difference in taste. If you make a pitcher of Kool-Aid and you put 2 cups of sugar in it, and it's syrup, or if you make a pitcher of Kool-Aid and you put a half a cup of sugar in it. For reference, the recommended amount on the package is 1 cup of sugar. So those are different concentrations of solute, the sugar, in the solvent, the water. We can measure this for any solution, and we're going to. And molarity, which is shown with a capital M, molarity, is the most common way to measure concentration of solutions. Okay, this is the most common. There is another kind, but it's not used very often. It's only used in one specific case. Molarity is used all the time. If you are going on to college chemistry, you must understand molarity. Okay? Everything in this lab, when we do a lab, all of your reagents are marked for molarity because you're typically using solutions. We don't typically hand you dry chemicals. You're usually getting an aqueous solution, a solution in water, and they're all marked for molarity. So you might see a container that says 1.0 molar or 0.5 molar or 0.1 molar. All right, so which of those 3 is the most concentrated? What does your gut tell you? What's your intuitive sense? 1 molar? Anybody want to vote with that? Are you 2 checking to commit to a position? Yeah, the 1 molar solution is the most concentrated. Okay? And all that a 1 molar solution is, it's 1, box this off, it is 1 mole of solute in 1 liter of solution. Okay? That's all a 1 molar solution is. 1 mole of solute in 1 liter of solution. Sodium hydroxide. So you've got that. If we wanted to make a 1 molar solution of sodium hydroxide, you would take 1 molar mass of sodium hydroxide, which is 40 grams, 40.0 grams. You would put it in a flask, and then you would add water up to the point where the entire volume of the solution was 1 liter. You don't add a liter of water. You do not add a liter of water. So let's draw those two scenarios. Okay, we've got our trusty Erlenmeyer flask. Okay, so I've got 2 Erlenmeyer flasks. I have 2 little massing boats with 40 grams of sodium hydroxide in it. I'm going to put the sodium hydroxide into each of the Erlenmeyer flasks. So now I've got my 40 grams of sodium hydroxide in the bottom of each Erlenmeyer flask. And to one of these Erlenmeyer flasks, I am going to very carefully add water until it's up to the 1 liter line on the flask. And then I'm going to put it on a stir plate, and I'm going to stir and stir and stir and stir until it's all dissolved. And I have 40 grams of sodium hydroxide in a total of 1 liter of solution. This is a 1.0 molar solution of sodium hydroxide, written like that, 1.0 big M NaOH. That's a 1 molar solution of sodium hydroxide. In this other flask, I'm going to do something different. I put my 40 grams of sodium hydroxide in, and then I'm going to take a graduated cylinder. Here's my graduated cylinder, and it's marked as so. And I'm going to put 1 liter of water in my graduated cylinder. And then I'm going to take that 1 liter of water, and I'm going to add that to the Erlenmeyer flask. And guess where my water line is going to end up? It's going to end up above the 1 liter mark. Okay? So what I have here is 1 mole of sodium hydroxide in more than 1 liter of solution. This is not a 1 molar solution here. Okay? This is absolutely not a 1 molar solution. Not 1.0 molar. Okay? Because I've got more than a liter of solution. It seems like a really subtle distinction, but that is the mistake you are most likely to make. Do not do that. Okay? Terrible idea. So why do we end up there with more than 1 liter of solution? Because the 40 grams of sodium hydroxide take up some space. They take up some volume. So if we add a liter of solution, then we have, or add 1 liter of water, we end up with a total volume of solution that's more than 1 liter. And with 40 grams of sodium hydroxide, it might not be a huge deal, but if you're making 20 liters of solution and you're adding a couple hundred grams or a few kilograms of your solute, that's a pretty big difference. That takes up a lot of volume, and so you end up accidentally overshooting the total volume of solution that you need. So if we break that down to its absolute simplest expression, molarity, big M, is equal to the moles of solute divided by the liters of solution, not the liters of solvent. That's critical. That's very, very important, not liters of solvent. So with that equation, you can rearrange this to solve for any of those 3 variables. And we're going to do some practice problems on 414. Okay, so this is sample problem number 1 on page 414. You are told that you've got 3.50 liters of solution, and it contains 90.0 grams of sodium chloride, NaCl. We want to know what the molarity is. Okay, a couple things we have to do first. We need to be in moles of solute. We're in mass of solute. So the first thing we're going to do is a molar conversion. Okay, so we started off with doing a molar conversion. We were given 90 grams of sodium chloride. We know that there are 58.44 grams of sodium chloride in 1 mole of sodium chloride. So we get 1.540041068 moles of sodium chloride. Now we have something we can plug back into our equation up here. Okay, so we have 3 variables potentially. We've got 2 of them, and we're being asked to solve for the third. Molarity is equal to 1.540041068 moles divided by 3.50 liters. Okay, so we use, of course, our whole number for number of moles. Divided by 3.5, we get 0.440011734 molar solution. Molar. Practice saying that word. We can have 3 sig figs. Yeah, we were given 3 sig figs and everything, so it is a 0.440 molar solution of sodium chloride. And that would be your final answer. Okay, questions on those? Okay, so here you're told that you've got 0.8 liters, that's 800 milliliters, of a 0.5 molar hydrochloric acid. How many moles of HCl are actually present? Well, we know that molarity is equal to moles of the solute over liters of solution, and we are going to rearrange here to solve for moles. Okay, we've rearranged by multiplying both sides by L. That gives us molarity times liters of solution equals moles of solute available. Okay, so we took our 0.5 molar HCl multiplied by the 0.8 liters of solution that we have, and we get 0.4 moles of hydrochloric acid of HCl is equal to our moles of solute. Not so bad. So this is a little bit more complicated because you're looking to find how much volume of a given molar solution you need to get the number of grams of reactant that are required. You need 23.4 grams of potassium chromate. That's the number here. And what you've got is a bunch of 6 molar potassium chromate solution on stock. How much of the solution do you need? Well, there's no connection to grams in that molarity equation. Molarity equals moles divided by liters. So you need to figure out how many moles of potassium chromate you're going to need. So you're going to set that up first. 23.4 grams, K2Cr04, molar mass of potassium. Okay, so we figure out that 23.4 grams of potassium chromate is a tiny little amount. It's 0.12 moles of potassium chromate. So now we're ready to solve for the volume in our molarity equation. Since this is the most common place to make an algebraic error, I suggest you go the long way around the barn. Get that out of the denominator, then divide both sides by molarity. So, we have rearranged our equation, and what we end up with is liters of solution is equal to the moles of solute over the molarity of the solution. So here's our rearranged solution. Let's go to the next page, and we'll finish the problem. All right, so we've got a 6 molar solution. We need 0.120494, etc. moles of our reagent. So we're going to take 6.0 divided by 0.120494, etc. And how many liters of solution? All right, so yes, I plugged the numbers in wrong. Rearranged it correctly and then screwed it up anyway. All right, so we're going to have 0.120494 moles divided by a 6 molar solution. What volume of solution do we need? Okay. Tiny amount of solution, 0.02008, etc., liters of solution. This is one that we would probably want to, if you were actually measuring this in the lab, convert into milliliters and measure. But yeah, it's a very tiny amount of solution. If you had a less concentrated solution, like a 1 molar solution, would you need more of your solution or less? You would need more of it, right. So the more concentrated your solution is, the less of it you're going to need in a case like this. All right, I will assign some problems like this that you will work on now to reinforce and cement, and I'll give you time to work.